So what I worked on over the break, mostly for fun and in hopes that it might provide some useful insight on Tendermint proposer election uh, necessities now and maybe other things we might want to verify in great detail in the future, was a sort of, you could call it formal verification of fairness of the Tendermint proposer election algorithm. So if you go to this repository, which is on my GitHub, so cwgo/tm proposer Idris, I'll also paste the link. Can I get back to that tab? There we go. You will see that the thing being proved has a particular type called fairly proportional, where if you have two proposer IDs, two proposer weights, and two proposer priorities, then some number n, natural number of rounds or block heights, and you have to provide initial proofs that the weights are positive and an initial proof that the difference in priorities is less than the sum of the weights, less than the sum of total power in sort of Tendermint parlance. Then you get a resulting proof or a value that inhabits the type saying that the count of how many times a particular proposer, the first proposer A, is elected in that number of rounds or heights, presuming constant, presuming no power changes. So this is just a simple case, is greater than or equal to the total number of rounds times the weight of the first proposer over the total weight, like with a slippage of 1, because if you have only one block, of course, you need to elect one of the validators proposer. So for some more context on what that means, if you have Idris open on your computer, just type Idris. You can clone this GitHub repository or not, just for this demo. So Idris is a dependently typed programming language, which means that types and values are both terms in the language, and the way in which you can manipulate them is very, very flexible. This comes at some costs. It is less efficient. You probably wouldn't want to write Tendermint in Idris, at least not anytime soon. And not everything type checks in all the ways that you would expect, in part because this is very much a research language. But the essence is there. So you can type like 2 + 2, which is a value, or you can type 2 = 2, which is a type. And then if I want to prove some type by sort of Curry-Howard, you just provide a value which inhabits that type. So if I want to prove that 2 = 2, the is like a typecast operator. So if we look at REFL, which stands for reflexive, REFL says that you can define equals between two terms if they sort of evaluate to the same form. So if I try to inhabit a value of type 2 = 3, it will fail. Because 3 and 2, which are just like syntactic sugar, obviously I don't know all of the syntax. If you try to inhabit a type which does not have which doesn't reduce the same value, it will fail the type check. So by inhabiting this fairly proportional type in this sequence of proofs, we're proving that this relation holds. Does that make sense so far? So in order to do that, we need to prove a bunch of much more minor things. So Theorem Provers, including Idris, which is one of a species, it's similar to Coq and Agda, either one or both of which you might have heard of. They use slightly different underlying type theories and have different syntaxes. Idris's syntax is close to Haskell. Both Coq and Agda have very complex Unicode syntax, which looks slightly more like math notation.
Could you backtrack? Just show like what exactly are we proving?
Yeah.
Like, what's the exact statement?
So the exact statement is a simplification of the algorithm that's actually in Tendermint. It's not the whole thing. And it's saying that in the two validator case, so we have one validator, call it A, another validator, call it B. We have increment elect many, which is the function that runs some number of rounds of proposer election and returns a list of elected proposers. So that's what we're taking the count over.
Okay, it's like a list of n different proposer elections?
A list of the results of that sequence of proposer elections. So we start with this state.
Number of proposer elections, right?
Yeah.
Okay.
We start with two validators, each with an ID, a weight, which is the same thing as power. I just didn't want to use P again, so I called it weight, and P for priority, and then a second ID, weight, and priority. And then given that initial state and some number of rounds, so the sort of semantic meaning of the fact that these are arguments to a function is that this proof ranges over all possible values of that argument. So this is like for any weight that is greater than or equal to 0, this we could provide a proof by inhabiting this type that this relation holds.
Okay, cool.
And the other thing worth noting here that is at least not currently implemented in Tendermint, is that in order to provide these very tight bounds, we need an initial bound on the absolute value of the difference in priorities. So if, for an immediate example of why that's necessary, if the two validators started out with like way out of whack priorities, one of them, which had the higher priority, would be proposer for like many rounds until their priorities got close enough to each other that they would then cycle.
So, so basically, by bounding the difference in their priority, you allow this fairly proportional to hold like for any n, except for 1, because that's where like the slippage is.
Yeah, that's true. I mean, you could write a proof with a less strict bound that only held for some n greater than an n naught.
Right.
In this case, though, instead of proving that it holds for n greater than n naught, we let n be 0 or 1, and the bounds we prove have a slippage of 1 block.
Right. So for here, it applies for any n, no matter how big or small.
Yes. With no power changes. So this does not incorporate any notion of many validators changing power throughout this process. This is like, if for any powers of these two validators, but once they start, they're constant, and then we prove over this epoch where the powers are constant.
Right. So if you didn't have the bound on the difference in the priority, then presumably the minimum n that this would hold for n naught would somehow be a function of that difference. Like if you wanted to actually.
Yeah, I mean, actually, so the number you would change if you like just went from this proof to that proof, the number you would change is the 1 here, because like you would have some initial sequence of blocks, which were whoever that was the higher priority proposer, and then it would revert back to the usual case.
Okay, cool. Carry on.
So if you, so to be clear, this is a proof only of the two validator case. It is a proof only of fairness over epochs with constant power. And I had to cheat a little bit, so not in anything critically important, but Idris does not have. This is like an academic language. It's not quite production quality. It does not have integer types that you can prove things over, because for some reason they decided to swap out their integers with like libgmp and just didn't write any proofs. So in the types file, I have a bunch of lines that say, really believe me. And these lines backdoor the type checker and tell it to assume things. In these cases, the things being assumed are just like field laws of arithmetic that A plus B is equal to B plus A. Addition is commutative.
So does this mean our this would work in like a modular ring then? If you have equalities, commutativity, associativity, negatives.
Yeah, probably.
Fancy.
There's nothing fundamental about like the integer type. But all of the meat is in the file called main. So by the way, if you happen to have cloned this repository, and if you just run make, it will pull up a REPL in which you can evaluate things. So for an example of the thing which you can evaluate, you can check that we have, in fact, proved this thing we say we've proved by running :t for show me the type of and passing in fairly proportional. And you see the same thing you saw over here. Except I omitted the net integer calls because those are pointless in the GitHub description. So if we open up, what I'll try to do, and feel free to stop me, but what I'll try to do is like explain the different components of this proof without going through. There's a lot of, like, as you can see by looking at this, it's extremely verbose. Every time you rearrange terms in an equation according to commutativity, or like add and subtract the same number from two sides in the equation, you have to write a line of interest. So it ends up being somewhat. Also, I'm not an expert, so it definitely could be cleaner by someone who knows this language perfectly well. But the important components of the proof. So first off, we have to define the proposer election function, which does the same thing the one in Tendermint does. It just does it for only two proposers. So we first add each power or weight to the current proposer priorities, and then we elect the proposer with higher priority proposer, subtract the total weight from that one, and otherwise we elect the second validator proposer. Then we have this function called increment elect many, which is written in a slightly weird mutually co-recursive way because it makes it easier to simplify the terms. But all it does is, if you pass it, so S is successor of some natural number. So if you started out with a number larger than 0, it will run increment elect and then run increment elect many recursively. So if you run this function 10 times with n equals 10 and some starting state, it will return the final state after 10 proposer elections and a list of the proposer IDs, which were elected proposer, validator IDs, which were elected proposer in each election in sequence. So then if we prove that the count of some ID is less than or equal to some number and greater than or equal to some other number, we're proving that the number of times a particular validator was elected proposer is less than or equal to some number or greater than or equal to some number.
Sorry, could you also increase the size in the browser, the font size?
Yeah, sorry. Is that better?
Yeah, much better, thanks.
So here we prove simply that the result of a proposer election is either that the first validator is elected proposer and that the priorities are changed in such a fashion, or that the second validator is elected proposer and the priorities are changed in such a fashion, which seems like a tautology, but this is a type instead of a value. So over here, this increment elect, which we've written, is just a function which takes an election state and returns an election state in the proposer ID. And now this result either is saying that the execution of that function is equal to, depending on what the initial priorities were, either something or some other thing. So now we know that it's equal to, we can like substitute out that equality in later proofs. Does that difference make sense?
Try that one more time.
So if we look at this fairly proportional function, this function doesn't if we pass it in n equal to, you know, millions and millions and millions, it's not going to actually evaluate increment elect, right? So we can't, we're not trying to prove, we can't prove for alls by actually running the function all of these times. So instead, we're proving that running the function increment elect is equal to either the resulting IDs, weights, and priorities if the first validator was elected proposer, or the resulting IDs, weights, and priorities if the second validator is selected proposer.
So the result either is trying to provide a type for the outcome. Is that right?
Yes, yes. It's saying that we know if we have some A where A is the a call of increment elect. So we're saying that if we call increment elect on these values, we know that the results will be either the first validator was elected proposer or the second validator was elected proposer.
Right.
And then Idris provides tools by which you can substitute out. So if you have an equality and you know A equals B or A equals C, then you want to prove something about A, then you can substitute out A for A equals B or A equals C and prove like it holds on the case B and it holds on the case C. These functions just prove that the weights don't change over multiple calls of increment elect. Okay, so yeah, so this is the first major component of the proof, which in English is saying that if we have the initial state, two proposers, and some natural number of rounds, we can provide, this syntax is that of a dependently typed pair, wherein the types of the type of the second element of the pair, which is this tuple, can depend on the value of the first element. So in this case, the first element we're providing is the tuple of the number of times the first proposer and the first validator and the second validator were elected proposer. So this is like NA, comma, NB. Just for strange reasons, you can't write it like that in Idris. So you have to write NS. And we say that we'll return two numbers in a pair such that the sum of those two numbers is equal to n. So however many steps are running the proposer election for, we of course have only elected that number of total proposers, such that the first number is equal to the count of the first proposer ID in n calls of increment elect. The second number is equal to the count of the second proposer ID in n calls of increment elect. And the difference in priorities is 2 times the weight of the first proposer times the number of times the second validator was elected proposer less 2 times the weight of the second proposer times the number of times the first validator was elected proposer. So to expand upon that, I don't know, key concept in this proof, at least as I've written it, and maybe there are other things to prove this, but a key concept is that of the difference in priorities between the two validators over time. So we start out with 2 priorities and they have some difference. And then we run a bunch of increment elect calls, which change proposer priorities, and we end up with some final difference between the 2 priorities. And we know what that final difference is as a function of the number of times each validator was elected proposer, because given that a validator was elected proposer, we know the relative change in the 2 priorities. So if the first validator is elected proposer, and I'll go back sort of the proof of this up here, if the first validator was elected proposer, we increment the first validator's priority by its weight and decrement it by the total weight. So a net decrement of the weight of the second validator. And we increment the second validator's priority by its own weight. So you see that's here. That's the weight of the second validator, and this is the weight of the first validator. So if the first validator's priority went down by WB, the weight of the second validator, and the second validator's priority went up by WB, the difference in the priorities viewed as the priority of the first less the priority of the second went down by 2 times the weight of the second. Does that make sense? And then the same argument applies for the second validator. If the second validator is elected proposer, the difference viewed as the priority of the first less the priority of the second will go up by 2 times WA, the weight of the first validator. So given that, if we know that the first validator was elected some number of times, we know that the difference will have changed in each of those times 2 times WB, and if the first validator was elected some number of times, in each of those times, the difference will have changed 2 times WA. So the total, the difference in priorities from the end state to the beginning state will be 2 times WA times NB, the number of times the second validator was elected proposer, less 2 times WB times NA. Follow so far? So
yes.
That, go ahead.
Sorry, there's a rhetorical question, my bad.
Just an emphatic yes from Dave.
Okay, cool. So why would we want to know that? It's not immediately obvious, but it will be useful if we know what the differences in priorities is if we can somehow bound it another way. So that other way is this function. So this function called diff for the difference in priorities says that if we start out with our state, 2 IDs, 2 weights, and 2 priorities, and proofs that the weights are positive, which of course they will be, and an initial proof that the difference in priorities is less than the sum in the weights, then we know that the difference in priorities after one call of our proposer election function will again be less than or equal to the sum in the weights. And basically, we know this by saying that let's look at the 2 cases. So we rewrite the increment elect function using the EQ either I talked about earlier into either the first validator was elected proposer or the second validator was elected proposer. And if the first validator was elected proposer, we know that this particular inequality holds between the priorities and the weights, because that would be what determines the first validator being elected. So we know that PA plus WA is greater than or equal to PB plus WB. And we know this initial bound, so then we can prove that the resulting proposer priorities will still satisfy that inequality. Sort of intuitively, if PA plus WB plus WA is greater than or equal to PP plus WB, then we want to prove the resulting difference in priorities. Since we know the difference will have gone down by 2 times WB, we want to prove that that's still, the absolute value of that is still greater than WA plus WB, less than WA plus WB. And since PA plus WA, since we know that WB, if we sort of rearrange this inequality, is less than or equal to PA minus PB plus WA, then we know that the inequality will still hold. It would probably also be useful to write this down on paper. But then if we have that bound in, so the result of this function is a proof that if we start out with a bound on the difference in priorities, calling this proposer election function will leave us with, in this case, the same bound on proposer priority. Now, this wouldn't work for any bound. It's only true for the bound. It would be true for a larger bound, but in this case, it's true for the lowest bound is the bound in of the total weights. Because if you have that with these inequalities, then you know that in order for one validator to be elected proposer, if you then subtract 2 times the weight of the other validator, it will still be within the same absolute value. So now that we have that, of course, that was over any state. So if we took any state and applied the proposer election function, we would get a state which still satisfied that bound in the difference between proposer priorities. So we can prove then recursively that if we apply increment elect many times in a row, so for some number n of rounds, and we started out with a bound in the difference in proposer priorities, we will end up with the same bound of the total weight. But now we have two quantities we can relate. So we start out with we started out over here with this total difference, saying that the difference in priorities is just analytically equal to this value. And then here we proved that if the difference in priorities initially starts as less than or equal to the sum of the weights, it will end up as less than or equal to sum of the weights. So given that, we know that the difference in priorities from the end to the start is less than or equal to 2 times the sum of the weights, because if you have absolute value less than x, absolute value less than x, and the difference of those two numbers is always going to have an absolute value less than 2x. So we plug those into this function fairly proportional, first getting out this whatever these NA and NB were, and then substituting in the analytical, the bound on the difference in proposer priorities to know that basically 2 times whatever we have here, right? So given the bound and proposer priorities, we know that the absolute value of WB times NA will be less than or minus WA times NB will be less than or equal to WA plus WB. So that's just substituting the analytical calculation of the difference in proposer priorities with the, substituting the bound on the difference in proposer priorities with the analytical calculation on what the difference of that difference would be over some number of blocks. And then we can simplify this inequality to get the bounds that we want. Does that make some sense? Let's see, what parts could I explain? Which parts were most unclear? I'll focus on those.
I guess to some extent, at least for me, maybe I'm lacking a little bit of an understanding of like the mechanics of what's going on here and what we're doing, and you know what's actually happening. So I've never really like worked with this or with Idris or really with any proof assistant. So it would probably just take a little bit of tooling around to start to understand it.
Yeah, I mean, you should definitely be able to understand the proof without understanding Idris. So I probably didn't explain that super well.
So maybe from a high level, you can kind of walk over the approach to the proof again. So it basically seems like you're bounding you're showing that, okay, you had these two relations, right? One is that the difference in the priorities is always less than the sum of the weights, and the other is that that the change in the sum of the priority and the weight is, sorry, I forget the first one.
So both the sort of two important related proofs are that the difference in priorities between the end, nothing about the weights, difference in priorities between the end and the start will be analytically equal to some calculation as a function of the weights and the number of times each validator was elected proposer.
Right.
So that's a function giving the difference in priorities as a function of the weights and the number of times each validator was elected proposer. And we want to solve for bounds on the number of times each validator was elected proposer.
Right.
So basically we rewrite this function. The other thing we know is that these numbers sum to n. So we rewrite this function in terms of one of the numbers to give like a function of the number of times that validator was elected proposer. And that is what this reduce inequality is responsible for. So here we have the difference in priorities, and here we have the bound on the difference in priorities, and like we divided out a factor of 2, which might be slightly misleading, but it hasn't changed. The idea is just that we started out with, we got from this inductive proof a proof of a bound on the difference in priorities. And given that we know a bound on the difference in priorities in the starting state and a bound on the difference in priorities in the ending state, we know a bound on the difference of those two differences because it's just the sum of the two bounds. And then, since we also know that the difference of those two differences is equal to this thing above here is equal to 2WANB less 2WBNA, then we can solve that equation for NA by substituting out NB equals NA minus N and translating the inequality to get all of the other things other than NA on one side.
The reason we're interested in the difference in the differences is because it gives us a relation to N.
Yes.
Right. And so the fact that we already have bounds on the differences, then we get a bound on the difference of differences, and because the difference of differences is related to n, that gives us a bound on n, and then we can prove the final statement, which is, you know, how many times each of them get to propose.
Yes.
Cool.
So, Chris, I have a bit kind of maybe unrelated question. So, does this like proving properties of proposer selection give you a bit sort of insight you didn't have before regarding how the proposer selection should work, like or like the way how you're proving things? Can this help in formulating the proposer selection in a more functional way?
I don't know about more functional. It is true that it gave insight. So this sprung out of a whiteboarding session by Ishmael and I before the break, when we kind of wrote down a very rough version of this, after which I tried to formalize it, but it didn't change much. The rough version we wrote down was mostly right. One thing that came out of this and came out of that rough version was the idea that we should have an initial bound on the difference in proposer priority. So we don't have this at the moment. And that's what leads to the cases like what we saw on that one testnet, where if the total power drastically changes and proposers have widely out of whack priorities, validators have widely out of whack priorities, one can be elected proposer for, you know, hundreds of blocks in a row until they get back in sync. So I guess one suggestion, which I believe Ishmael put up in a PR already, is to renormalize the proposer priorities if the total power changes, such that they would get adjusted back to be within the sum of the weights, or it could be like 2 times the sum of the weights or something.
But so for me, what is interesting that you are able to reason here more or less for infinite number of proposer selection. And so I'm wondering if, like, given some initial state, we are able to sort more or less formalize like what would be the proposer, I don't know, after k instances of selection. Because if you're able to have these written also as a function, because at the end here you're proving this in kind of functionally by not really by proving that something will be executed after even like infinite amount of time. That this might help us to also formalize it in a way which is also kind of clear here. Because right now, go ahead.
The tricky part in practice, I guess, will be that there will be power changes, at least with some frequency. So,
yeah, sure. But the thing is that as a starting point, and I think anyway, regarding fairness, it's always eventual fairness. So if you have a frequent the changes to the validator set anyway, you can't provide any fairness short term. So it always needs to have some stability so we can have fairness. So somehow the starting point is that given validator set and then set of invocation, we have some fairness guarantee. And so what is somehow for me, let's say, doesn't or it smells bad or it looks fishy, is the way how we are currently doing this with this just incrementing or decrementing this proposer priority. Because I mean, it's amazing what you did here, but I have a sort of intuition that if we make it a bit more complex, the proof will be even more complex. And I don't think that this is not necessarily just the way how proof is structured. Maybe it's more just how current implementation works or proposer selection. And so it's just my intuition, but I might be wrong completely. So I think if you're able to formalize in a way that given a state, we can compute the sequence of selection, it might also be more easy to prove this. But it's just
I mean,
any proof for this.
We do that. That is like what we're proving over is we're proving the count of a particular proposer's number of elections over some sequence of elections, which is deterministic as long as there are no power changes. So. Maybe what I could do, which would be helpful, is to like write up some LaTeX, maybe with you, Ishmael, once you're feeling better, to go along with this, to like explain it in English. Because a lot of this code is not, I don't know, it's not necessary to read to understand the proof. Like all this function does is solves for a particular variable in an inequality. So.
Yeah, this would be super useful if it's not like a lot of work for you guys. This I think would really be helpful.
I do think it's useful to have in Tendermint a like dumb proposer election, even if we eventually get a VRF or something, a dumb proposer election algorithm that has very clear properties. Some people might want that.
Properties without power changes aren't that, like, I don't know. I'm dubious how useful it is because like, the attacks all have to do with power changes.
Yeah, I mean, it seems like whether or not attacks are enabled by power changes is like solely a function of what the initial priority is set to, right?
Is that in the two-party case, or in the two-party case, I agree, but when you have more parties and you have more of them varying dynamically, it's not clear to me that that's all that matters.
Have you thought about how to extend this to like K validators?
Yeah, I've thought about it. I haven't had a chance to do it yet, but I've thought about it a little bit. It's not difficult to provide a similar function of like the total difference in priorities. It is it'll be a more complex case to prove that the difference in priorities is less than or equal to the sum of the weights.
In the worst case, you can prove it's cyclic and then show that like here's the amount that goes to proposer in the cycle.
Yeah, it might be easier in the multivalidator case to prove a ratio like directly prove a ratio between two proposers, which would then be enough because you know that the sum is the number of proposer elections. So if you can prove like between any two proposers with a given ratio and weights, the difference between the number of times their elected proposer is like bounded by the ratio and their weights. So I'll try to do that.
Awesome. And you think you'll be able to do like changes like dynamics as part of this, or
power changes?
Yeah.
Well, the trick, I think, certainly in principle, yes. The tricky part is articulating exactly what it is we want to prove under that case.
Yeah.
Dave and I discussed this a little bit. I don't know if we came to an exact conclusion.
The last column was you agreeing with the thing I proposed. I don't know if you've had changes since then.
Maybe I did agree then. What was the thing you'd last proposed?
Essentially that you have an epoch size, and so there's no power changes within epoch size. And then between epochs, you allow arbitrary power changes. And then you say that for all validators, like there's like an infinite summation of like blocks of like their power per divided by the epoch's total power times epoch size. And like you say that the amount they propose is like according to that fraction. After
This
a
is the
certain
last
number,
thing
like
Yeah, I get this, but I don't think it actually holds for our algorithm. Because if you have like...
oh no, I don't think it holds for our.
Well, okay.
Okay, I don't think our algorithm is safe. Yeah, I'm very convinced that our current one is not will not meet that safety criterion.
Is that because we're not using epochs?
No, it's because when we reset...
And
Go ahead, Dave.
oh, I was about to say what you're saying. So,
You guys are too polite. One of you please talk.
Oh, okay. It's because when a new validator joins the validator set, we reset their priority to negative total power. So if like validators are being anti-rational and just keep rejoining the validator set, they'll never be elected proposer. Or like they'll be elected proposer much less frequently than they would have been.
oh,
Right.
there's also some more issues. I think like
But isn't
that only helps.
if they leave and come back and leave and come back, and as a result, they never end up being the proposer, that seems okay.
It is okay, but it means that we can't prove this.
Right. Or that we have
There
to
are other issues as well.
to accommodate. But yeah, sorry, go ahead, Dave.
Oh, the whole idea was to combat the fear, like, okay, I'm just gonna leave, I'm just gonna unbond everything, then rejoin again, and to like boost my power. Like, okay, so say I have two validators, and so I have one validator is about to propose called A. Then I have this other thing, this guy B, who's near the bottom. So I have B leave right before A proposes. So A gets decremented by a smaller value, but in the block that A proposes, you bring back B. Like B bonds again. So what the thing we did like fixes that when you do a 100% unbond. But okay, now you're 99.99% unbond. This does nothing.
Okay,
We're back
but I
where we
still don't
started.
agree that that's actually a problem because you lose out of one block of gaining priority for B.
Yes, but we don't have it. Your priority stays the same. So by virtue of you expecting everyone else to decrease again, it doesn't matter.
What do you mean your priority?
Like you can think of
I don't know what you mean.
maybe you're right. Maybe it doesn't affect long-term distribution.
Change your
For
weight,
me?
right? So your priority doesn't change. It doesn't stay the same if you change your weight.
No,
You're
your
right.
priority.
A gets more. A isn't decremented by as much. The amount by which A is decremented decreases by the amount of tokens you unbonded from the second validator just prior. But it's also true that the second proposer is the second validator is incremented by, decreases by the amount of tokens you unbonded from it.
But if we allow arbitrary state changes and you move that from B to A, and so A is proposing with more, so you still get that reward. Then so A decreases by less, then you re-equalize again.
I see.
So this is true. Like this is an attack. If we
back and forth between two validators in order to take advantage, like to impact the proposer priority.
Yes,
which
we can always assume that you
happen because we don't allow like repeated redelegation.
Right. You can go one way, but you can't get back without unbonding.
But it's true that it would be nice to have.
So the plan was originally.
Go ahead.
Originally, as far as I understood, the plan was to eventually allow infinite redelegations if we figure out how to code it efficiently. So this is a practical limitation, not an issue with our theoretical proof of stake model. Sorry, this is an issue in our theoretical proof of stake model, not the one we implemented.
I understand. So okay, so to address this, to address it theoretically at least, what were you saying we need to do to change? We have to introduce epochs and somehow change the way we assign priority.
I think not. I think we just need to do what we're doing at the moment, which is setting the initial priority to negative total power, so that you get extra punished. That's the idea. If you leave but that doesn't solve the partial unbond rebond case. That's true.
Won't that violate the bound on the difference in priorities? I guess that's okay. If it might be harder to prove, but it means someone who just joined isn't subject to the same guarantees as someone who's been around for a while with respect to.
Yeah, that's true.
Proposer.
I mean, there will be a slightly larger bound, so you could just prove a difference of 2 blocks instead of 1 block. But
right.
I think it would be better to not to just delay them before they join the voting set. But I'm also not concerned with the people who are leaving and coming back, because just ignore the people who leave. Just say they go down by 99.99%. It's effectively the same. They skirt the that initial setting.
Yeah, that's true.
So how do we handle those?
I don't know. Randomness. Or we could
No. I mean, that's not. One way of handling them would be to delay total power calculations by 1 block.
Oh, but then I should do it over 2 blocks.
If A is elected proposer again.
No, but if I assume my transactions will get in, then I can always time it such that B.
But then you're getting extra punished.
I see. So this is why. So Jarko,
that's true.
You made a suggestion in Slack today that would have gotten around this, if I understood what you were saying, by basically saying that your chance of being proposer, instead of it being based on some stateful, some additional stateful thing like a proposer priority, it's based on kind of the number of times you've proposed before and some other information. Is that right? Would that kind of approach avoid these kind of gaming issues?
So I was more trying to because I was for me it was not really clear exactly this case. Like when we added the new validator, we set this proposer priority to a very negative number, and so for me it was not really clear what is the property we ensure with this. I have the intuition is that the new validator should somehow have less chance to propose than the guys who are there, but I'm not sure that this is really the best way to achieve it. So I was trying to reason the other way around. Say, okay, if you are for a long time part of validator set, then you should gain by doing this and not being punished for joining. And also. It's just a kind of very initial thinking that if we are just adding some metric to the validator set, then we could have a function like really a function, which based on those data tell you, give a rank of each proposer. And if we tune correctly the parameters of this function, then we could have more or less the same fairness guarantee like we have now. But the difference is that given validator set, I have a function which tell me, okay, this is the proposer. And then when we change validator set, some of those metric will change. And then we again have function, which tell us exactly what is the thing. So given a validator set with some state, we know how the next case selection will be. If the power does not change.
That seems like what we already have, though, right?
It's true that it's similar. The difference might be that we might be able with a function to sort of tweak it this way or that way. Maybe, but yeah. After I was thinking, after I wrote this, I was thinking a bit more, and I also realized that it's somehow close to what we have. So it's still not what I'm kind of hoping to achieve. So. But I somehow have a feeling that the way we are doing it right now looks like a hack. We modify some things here, and then it fixed one case, but then we don't really have a clear guarantee overall. So and we keep patching it around, and maybe the solution is really to sort of have a clean way to do it once, and then it somehow holds for any case. But I don't know how to do it. So I failed so many times to doing this. So
okay. Well,
because also I discussed with Anka a bit about this, like from the application point of view, like arbitrary application using Tendermint. What is really the semantic current proposal selection provides? Like this behavior is I guess like Cosmos specific, like the fact that you add a validator and then it gets negative total voting power. Like for arbitrary Tendermint application, what does it really mean?
Yeah.
Like why it behaves this way?
Right. This goes back to the discussion about changing ABCI to support proposer orders, right? So for instance, like along with the end block, you return a list of proposers, and that would get used at the next height for the proposer selection. And that way you can move the selection algorithm completely into the application if you want it. It doesn't quite solve the problem. It kind of punts it over to the application, but at least it doesn't force a particular algorithm upon you, and the app can separate the proposer selection from the voting power and kind of do something different. But it's kind of a separate story.
Yeah, that's why I was thinking like this was more or less along this proposal I wrote today. So given set of validators with the voting power and some history, and historical data are captured deterministically. So how long you are part of validator set, and some additional quality we could add there. Then we could compute rank, and so application could also all completely override rank. And so this is something also which potentially could be externalized. It just need to be deterministic. And but fairness is something which application might be having completely different view on fairness.
Right.
So I might want to select more guys who actually are able to collect more transactions. Maybe this makes more sense for some application, or which has better connectivity to other guys or whoever, whatever.
Yeah, it could even be like part of the proof of stake reward system, like you bid to be proposer or something.
Right. Yeah, I started thinking about using like auctions for proposers and stuff like this. Anyways, I think we should look towards wrapping up this discussion. I guess kind of in conclusion. Sorry, Chris, I had one more question I wanted to ask, which was why. If you could tell us maybe a little bit about how and why you chose Idris rather than Coq or Agda, or even a like model checker, like TLA plus or something.
I'm not familiar enough with TLA plus to have compared it. I don't know if, does it have like full dependent? I knew Idris was expressive enough to prove what I wanted. So are Cock and Agda.
Is there some reason you chose Idris over Cock? Doesn't Cock have better support for like proofs over integers?
It might. I'll try out Cock. I tried none of them, so I don't think I made a particularly in-depth comparison. Idris has a reputation as being slightly more practical, and there was a very good piece of documentation I found on it, but it would be worth trying other things too.
Cool. Okay, good to know. Okay, great. So I guess, I guess kind of in conclusion, wrapping this up, respect to proposers, like, I think really what we just need is something that is going to be like good enough where we can clarify the guarantees somewhat reasonably, and that can be the default proposer selection in Tendermint, or now deterministically. Down the road, I think we want to expose the ability for applications to more directly influence the proposer selection, and of course, there's also proposals around incorporating randomness. So I guess that kind of spells out a little bit of the roadmap for this. But for now, Chris, that it was really great work. Really, thanks for the presentation. Something new for all of us, I think. So really cool to see that. Hopefully, we can do more of this kind of formal specification and verification. I think that's quite exciting for everyone here. So thanks a lot, and we'll see you next time.
Thanks a lot, Chris. Amazing presentation.